disappointed last year when NASA retired the space shuttle. But what they didn't know is that by the time the shuttle was retired, NASA already spent several years researching and designing its replacement, the Orion Multi-Purpose Crew Vehicle. The concept of the Orion is similar to the Apollo, except the Orion's goal is to land safely on both land and sea, which makes designing carefully the parachutes for the Orion very important. My work focuses on computationally modeling the fluid structure interactions involved in spacecraft parachutes. It's a low-cost alternative to empirical methods, but it's complex and challenging. The parachute fabric and the parachute itself, the mass is very low compared to the air masses involved in the dynamics of the parachute. We also must model the flow through several hundreds of gaps and slits in the parachute fabric itself. In addition, some parachutes are designed to open incrementally over several stages, causing drastic changes in the parachute shape from one stage to another. Accurately addressing such challenges numerically requires a robust, fully coupled fluid and structural solver capable of efficiently solving millions of nonlinear equations within each time step. Our team uses several computational techniques that has developed and improved over the years to be more accurate and have proven effective in modeling a wide array of spacecraft parachute designs, flight conditions, and loadings. Results are briefed directly with the NASA engineers at Johnson Space Center for design and then Orion's parachutes. This will ensure that for far in the future, NASA has methods to ensure our astronauts have a safe, gentle ride home. Thank
you. Chad Rose.
The current engineering approach to robotic rehabilitation for spinal cord injury and stroke patients does not successfully restore quality of life. State-of-the-art rehabilitation robotics can only restore gross muscle movements and not the finer detailed movements such as buttoning a shirt or unwrapping a candy bar. The solution I'm proposing is part of a collaboration with UT Austin and is a novel combination of a hand and wrist exoskeleton. This exoskeleton will have the capabilities to break down these finer movements required for quality of life and break them down into their basic components. Breaking down these motions and integrating the hand and the wrist into one exoskeleton will require a new level of miniaturization, precision, and integration. Currently, this project is in the process of building a finger and evaluating the design of this prototype. This finger can readily be modified to actuate the entire hand, at which point we'll combine the hand with an already proven wrist exoskeleton design. At this point, we will implement these broken down motions into a rehabilitation technique. Hopefully, not one day, not too many years in the future, this exoskeleton will be restoring the quality of life to these patients and allow them to open up those candy bars. Thank you.
Sagar Neil for Kiyasta.
Soldiers returning from war, say from Iraq or Afghanistan, sometimes have their arms blown up. Now, some of them come back and get artificial arms, powered prosthetic devices or an arm, or an artificial arm. But even then, they lack doing activities of daily living, such as simple tasks, such as picking up a glass of water or a phone or ice cream on an ice cream cone. The reason they can't do this is because the fingers of their artificial arms or the grippers of their artificial arms lack the sense of touch. They only have to rely on their vision to pick objects. What I'm working on is to restore the sense of touch by producing vibration signals on the residual arm. That's the part of the arm that's still there. The way I'm trying to do this is by making the amplitude of vibration proportional to the grip force sensed by a force sensor at the end of the artificial arm, at the end of the gripper or the fingers. Now, that way, the amputee would know how hard he's holding onto something, if he's crushing that object, or if the object's about to slip and fall. Now, once this research is done, what I intend to see is amputees picking up, grasping and lifting objects just like non-amputees with equal ease and efficiently. So that's what I intend to see happen in the near future. Thanks.
Vinay Chopra.
Currently, surgeons are using robots to perform complex operations with few tiny incisions. The surgeon uses a local robot to command a remote robot which performs operations on the patient. The remote robot is synchronized with the local robot and transfers surgeon's actions to the patient. In the present setup, the surgeon only gets a visual feedback of what is going on inside the patient. My research focuses on adding a sense of touch that will allow the surgeons to not only see but also feel what the remote robot is doing, virtually transporting the surgeon to the site of the surgery itself. This added sense of touch will make the robotic surgery more lifelike and allow the surgeons to feel the forces as they do a certain task. I intend to develop a safe interconnection between the human operator and the remote robot so that the operator can feel the forces and actions of the remote robot. This technique can also be applied to applications other than surgery, such as control of remote control of unmanned vehicles, where operator can both see and feel the remote place as they interact with it. Thank you.
Spencer McIntyre.
If you've ever seen a 200-foot-long wind turbine blade being carried down the highway, we're seeing hundreds of turbines in full rotation in a wind farm. You have some idea of the massive scale and complexity of a modern wind turbine. Full-scale, accurate models of these wind turbines is in high demand, and to meet that demand, computational methods face the difficult challenges of complex geometries, moving and stationary components, and fully turbulent flow on the wind turbine. My research with the team for advanced flow simulation and modeling involves modeling a turbine using the team's space-time finite element solver. More specifically, my research deals with building the turbine mesh and defining the turbine rotation using non-uniform rational B-splines, also known as NURBs. Using NURBs in space, the actual airfoil profiles can be exactly represented along the length of the turbine blade at different cross-sections. NURBs allow the generation of the smooth geometry that is necessary for an accurate aerodynamic analysis and can be easily modified to represent any wind turbine design. Another crucial aspect of wind turbine modeling involves an accurate representation of the turbine rotation. Using NURBs in time, we're able to exactly represent the circular motion of the turbine with very few input parameters and eliminate the error from discretizing a circle into individual line segments. Using NURBs for geometric modeling and definition of the rotation improves the accuracy and efficiency with which the finite element method can model wind turbines. In doing so, my research contributes to the development of wind turbines as a source of clean energy.
Sean Estrada.
In the year 2000, medical-related errors was documented as the 7th leading cause of death in the United States. Statistics like these added to in the development of medical simulation as a means to help improve surgical training in specialties such as cardiovascular surgery. While the technology and robustness of these devices have grown, unfortunately there still lacks standardized and quantifiable methods of both determining skill level and providing performance-based feedback during simulator-based training. Objective measures are important to validate medical simulators both as effective teaching tools and to provide resident more reliable and immediate feedback to facilitate on-the-spot corrections. My research focuses on finding these quantifiable measures. To do so, I will use hand and tool tip motion data obtained from cardiovascular surgery simulators to derive metrics that will help to characterize novice versus expert behavior. Additionally, I will identify performance-based measures such as smoothness of movement that correlate to existing procedural outcomes such as total X-ray time. Once found, these measures will be evaluated during surgeries with live patients and should lead to safer practices in the operating room.